let's continue to tie our ideas of rotational motion back to topics we've previously discussed. So when a force or a torque causes a body to accelerate, the work done causes a change in kinetic energy, and that's our work energy theorem, right? For linear motion, work is the change in kinetic energy, which is the final minus the initial kinetic energy. And of course, each of those kinetic energy terms is 1/2 mv squared. Rotational motion, same relationship. Work equals the change in kinetic energy. Now, if we're just dealing with rotational motion, then work is the final rotational kinetic energy minus the initial rotational kinetic energy. And writing all of that out, that's going to be work equals 1/2 I omega F squared minus 1/2 I omega I squared. And so that is what our work energy theorem will look like if we're just dealing with rotational motion now. We can expand this to the definition of work for linear motion. Work was force times the displacement. For rotational motion, work is the torque times the angular displacement. And lastly, the definition of power, the rate at which work is done. For linear motion, power is work over time, which for the special case of a constant velocity, we could say that's equal to the force times that constant velocity. And we're going to have a similar expression here for power. Again, it's work over time. But then, if we're dealing with a constant rotational velocity, then we can write that as torque times that angular velocity. And so those are some more definitions of work and power tied to our ideas of rotational motion.